I covered put, get, and accumulate, which again were the operations that were added originally to the MPI RMA. And you can do an awful lot with those. But for example, one of the things you can't do with accumulate is read the data and then modify it. You can't do an atomic read, modify, write operation. You can do, accumulate does a modify, write, but it doesn't give you either the before or the after value. And I should say, the names of these routines, MPI put, MPI get, something I should have said before, I in fact argued when we were defining these that they should be called I put and I get and I accumulate, because these are all non-blocking routines. And I will say, as in a I told you so moment, shortly after the MPI RMA was released, I read a paper which had been published where the authors had gotten it wrong and the reviewers hadn't caught it. They thought that put and get and accumulate were blocking. So that's the other thing to remember, is all of these are non-blocking operations. So, which also then leaves open this question we have not yet gotten to, is how do I complete them? So one of the things that was added in MPI 3 was this routine, get accumulate, now even more complicated. But again, just like the others, if you just think about what is it that I have to move and then what are the tuples for each of those arguments, I've got the data that I am sending that's going to be combined using that operation. So that's the green stuff with the orange operation to the destination in blue. But because it's a get accumulate, I'm also going to return the data before the modification. And so that's the red specification there. So there really are only a couple of arguments here. It's just that some of those arguments have 3 parts. Okay, so you get the original data again. So it does the read, then it does a modify with the op, and then it stores that result. So think of it as read, modify, write. That's an easy way to remember, well, do I get the before or the after data? You always get the before data. Okay. There are also 2 additional operations that can be applied. So, we could be looking at just like MPI sum, but 2 operations were added in the MPI RMA. One of them is MPI replace. So what does that operation do? That just takes the data in green and it replaces the data specified in blue, which looks a lot like a put. And we'll get to why you would actually want that. The other operation is a no-op, which means I don't overwrite the data in blue, but I still do the get. And again, why do I do that? We'll get to that in a minute. Okay. As I mentioned, there are also 2 sort of special cases. The first one is fetch and op. So look at fetch and op and compare them to what I've been showing you for these operations. What is different about the fetch and op in that specification?
Compare address?
Sorry?
The compare address?
Well, yes, but let's just look at the fetch and op. Look at the arguments. What's different about those arguments than, say, what the get accumulate that I just showed you?
No target address?
Sorry?
There's no target address.
Well, there's a target rank and a target displacement, but what's missing?
There's no count.
Yeah, there's no count. There is a single data type. There isn't a data type for each one. So this does a single element of one data type. So and it's a get accumulate, but it's a get accumulate specialized to a count of 1 and the same data type everywhere. And so this, for example, remember I mentioned, say I have a counter. I have a global counter. I want anybody to be able to access the counter and increment the counter. And further, I want to make sure that there's no race condition in that increment. So accessing the value, incrementing the value, updating the value, that read, modify, write has to be an atomic operation. If it wasn't an atomic operation, there's a possibility that several processes could come in and, for example, read the same value of the counter. And I'm assuming that I want a counter that is incremented by, say, 1 each time it is used. So fetch and op will give you that kind of an operation. And how that's implemented, you hope that the hardware, the networking hardware, the system hardware makes that efficient. It's up to the MPI implementation to make it as efficient as it can. Some hardware, in fact, provides these sorts of operations because it's a very powerful one. And so this was provided because you want, when you're doing something like that, you want it to be simple. You want it to have the minimum sort of overhead. You want to encourage the implementations to optimize it. Fetch and op doesn't do anything that cannot be implemented with get accumulate. But it's there to encourage the implementations to do a good job on this special case. And it's there to reduce some of the inevitable library overhead, because the generality of those other routines comes with a cost. It's a small cost, but it does come with a bit of a cost. Compare and swap is another important and powerful, although I do want to warn, tricky operation that's often used in some shared memory algorithms. Who has heard of the ABA problem? Okay. So none of you should use compare and swap. What compare and swap does is it compares a value, and if that compare value is equal to that remote value, it swaps, it reads out that old value and reads in and stores in the new value. So for example, it's a really powerful way to add to the end of a list if you think you know where the end of the list is, because you can look and say, if the pointer to the next element is null, then swap in this address because that will then link in the right element. The ABA problem is a problem that comes about when you're doing these comparisons and your algorithm might have the case where you're looking for A, and if you don't find A, you'll do the B, but somebody else might then also be looking for the A. And you can still have some race conditions with compare and swap, depending on how you're using it. So you can use compare and swap in some cases. In other cases, it has a very subtle race condition. So you can Google the ABA problem if you're interested in that. Anyway, so this, again, is a powerful tool. There's some systems have hardware to implement this inside the processor. So this is a powerful way to program even shared memory. Okay. So why those special operations that MPI replace, the MPI no op? This again comes down to the fact that MPI is a very low-level specification. It is trying to allow you to access the fastest possible performance, and it does that by making some trade-offs that you need to think about in your algorithms. So one issue, one thing to bear in mind in modern networks is something you might think is sort of obvious, like say, I send a message and then I send another message. I might think that, and from the same process, I mean, so the same thread, same process, same node, everything. I might think that, well, message A was sent first before message B, of course, and they're going to the same place. Of course, message A will arrive before message B. Unfortunately, that's not true. Or it might not be true. And why might it not be true? Well, think about what happens with the data. So the data is sent. What does that mean? It goes from the memory on the node into the network interface, into the network. And you've seen some diagrams of these networks, and say it starts running through the network. Well, what route does it follow? Well, it might have a deterministic route, in which case I can say, yes, if message B enters that same deterministic route before message A, then of course it will get there after message A. But what if the system is smart and is able to reroute data around momentary items of congestion? It's doing things to make the data communication faster. Then two pieces of data coming from the same place, going to the same place, may not follow the same route, may not arrive in the order in which they were sent. And requiring that they arrive in the order of the sent, again, like we talked about this morning, is an extra synchronization. If you need it, you need it. But if you don't need it, requiring it will slow things down. The same thing is true in shared memory on a lot of systems. So a classic mistake that will work on some architectures just because they have a bit more requirements and ordering, but it's not in C and it's not in Fortran. So say you're in shared memory, just to make this sort of simpler. I'm in shared memory, I'm not doing any of this network stuff, and I'm copying data from one place to the other, and I want to know, thread A is copying the data, and thread B is going to use it, and thread B wants to know when it can use it. So one thing that a lot of people have done in their codes is they have a sentinel. So they write all this data, and then they write a last bit of data, and the thread that's going to use it has been watching for that data to be written. And once that data is written, it says, oh, everything's here. Unfortunately, that's wrong. The languages do not guarantee that ordering. Some architectures do, others do not. This is further, from a numerical standpoint, this is among the most difficult kinds of bugs to uncover. Why? Well, think of what's happening. Say I'm using this for a Halo update. What happens if I end up reading the wrong data? Well, I'm probably not reading terrible data. I'm just reading the data from one time step ago. So I'm adding a O of delta T error. This is always the worst thing. I'm adding a little bit of an error as opposed to something that causes the computation to obviously be wrong. If it's obviously wrong, I know there's a bug. Here, the data is just inaccurate. So the same thing can happen in MPI for the same reasons. We're trying to allow algorithms to optimize this. And for algorithms where that ordering doesn't matter, that all that matters is I'm going to do something in which I haven't even gotten to yet that will say I've got all the data, that's fine. That allows me to take advantage of, for example, these adaptive networks that give me better performance for moving the data. And it's the same thing in shared memory. Not having those ordering guarantees means that the shared memory system is simpler, faster, uses lower power. Okay, so what does all this mean? So this means that the put-get operations are unordered. Well, that means, for example, that if you put two values to the same location, who knows what you get? Actually, in MPI 2, we said it's an error. In MPI 3, we said we don't know. It's a subtle difference, but an error means that, for example, the MPI implementation could generate an error and abort. In the case of we don't know, it's just we don't know. The accumulate operations, though, they are ordered and they are atomic. And so if you want to do a put that is atomic, you can do accumulate with that MPI replace. If you want to do a get that's atomic, you do with an op that is the MPI no op. You can also, using that info, inform the MPI implementation that you exactly what kind of an ordering you need. So that's the now beyond expert tuning, but it's an example of how the info is used. And again, it's an example of the sorts of things you need to think about in the use of the one-sided operations or in shared memory. Okay. So what you should be thinking about here is simply be aware that you have to be careful what you assume happens versus what is actually required, because some of those things are in tension, and implementations, again, either shared memory or MPI, that are trying to give you the maximum possible performance are likely to do things which are valid in the programming language, but might be a little surprising. There is if you want some nice examples of that, there is an article I think in the Communications of the ACM probably a decade ago now, titled something like, you don't know jack about shared memory or variables. I encourage you to read that because it does give you some examples of things you need to think about. Okay. So this is just a few examples. If you're doing concurrent accesses of any kind, updates, reads, or whatnot, don't use put and get unless you're okay with things being undefined, which some algorithms actually allow. If you need the ordering, you need concurrent updates, you can do that. You just have to use the accumulate and the get accumulate, which gives you these options where internal to the implementation will have to work a little harder. It means that they're likely to be a little bit slower, but they have these more properties. So again, this follows the sort of theme here is that you want to look at your application and where you are performance critical. You want to be careful not to overspecify what you require. You don't want to overspecify the ordering. You don't want to overspecify the synchronization. Okay, so we've talked a lot about moving the data. You still don't know how to know that the data has been moved. So now I'm going to talk a little bit about that. So as with shared memory, the question is when can you touch the memory? When is the data available? How do I know it's available? MPI provides 3 models. I'm not even going to say very much about this middle one. I'm going to talk just a teeny bit about the first one, and then we'll focus on this last one, this lock-on. So the fence model, it's called an active target model. And let me ask, how many of you know about the bulk synchronous programming model? Okay, not too many. Well, this is another historic artifact. The bulk synchronous programming model was an early programming model. It was built around one-sided operations, but with and also around a performance model as part of that. So it was in some ways ahead of its time in terms of thinking about the performance as a core part of the goal of the language. One of the operations for the one-sided was a fence. Basically, say I do a bunch of puts and gets, then all my processes can do a collective operation, we'll call it a fence. And at the end of that operation, all of those puts and all of those gets will have completed both locally and remotely. So that so for example, the gets will have gotten the data, the puts will have completed both at the target process in the sense the data is already there, and at the origin process in the sense that that buffer is no longer needed by the put. Remember, those puts are non-blocking. Okay. This was a really important model in the MPI-2 era because a number of computers implemented the fence operation in hardware. So it was really, really, really fast. That has sort of fallen into disuse for a number of reasons. One is, as you will be seeing, for large scalable applications, the bulk synchronous model is very sensitive to all sorts of things that limit performance, whether it is load imbalance, whether it is impact from scheduling irregularities on nodes, impact from thermal effects, all sorts of things. Particularly at large scale, the bulk model, the bulk synchronous model is considered not as appropriate for highly scalable systems. But that fence model was really convenient because it was really easy for you to write these codes. You would write a code, you'd get to a point where you needed to move data, you would describe all of the puts and gets and everything else, then you would do a fence, everything was done. Okay. We call that an active target model because I've been talking about these one-sided operations by saying that one process does like the put, or one process does the get, and it affects the data on the other process. So that other process doesn't need to make an MPI call. And I'm going to put a little asterisk up there. We'll get back to that. In the fence model, it's true that no other process needs to make the call to match the data motion, but that fence call was collective across all of the processes. And in the MPI sense, it's collective across all of the processes in that window object. And so in that sense, even though the specification of the data motion is one-sided, the specification of the data synchronization is collective. Okay. The post-start complete wait was an attempt to provide a more scalable option where you just talk about the neighbors. You can think of this one as an early form of the neighbor collective, sort of, that did not work out very well in practice. So we won't say anything more about that. The last one, which is the one that I think is the most important now, is one called a passive target, or lock-unlock. And here's another place where I usually say in every version of MPI, there's some place where we picked an absolutely awful name. And awful in the sense of it doesn't mean what you think it means. In MPI 1, it was extent, which is really stride. In MPI 2, it was lock and unlock. Because lock and unlock is not a mutex. It's not a lock. It's not like a thread lock. It is really a begin. Lock is a begin, unlock is an end of an access from the target process. Lock enables the target process to start making put and gets. And the unlock is the point where it says everything has to complete. That was in MPI 2. In MPI 3, we added a version that is a lock all and an unlock all, which allows you to do this essentially like you would do with fence. but the synchronization has a finer grain control. And I'll say a little bit more about that later. You'll see a language in the standard about access epochs and exposure epochs. So the access epoch is the origin process when it can start doing things. The exposure epochs is the remote process making its memory available. There's some definition of this. In fact, one of the strengths of the MPI RMA specification is it's actually quite precise. Honestly, this has been a weakness of some other shared memory and remote memory specifications, which have tended to brush under the rug the complicated details, which meant that some things, programs would work on some machines and not work on others, and they were both right because the specification was vague. The MPI specification is much more complicated, but it's also much more precise. Okay, so I think I covered a lot of this about fence. It is a collective model. It both starts and ends these access and exposure epochs. Formally, one of the things that's a little different from the bulk synchronous model is you're supposed to do a fence to start the epochs as well as end it. So you would do a fence at the beginning and a fence at the end. Coming back to something that we were talking about in the morning, you have to be careful again. Fence has barrier semantics, but the semantics are just for the RMA operations. So for example, even though the implementations are likely to do a local memory barrier for shared memory, that's not part of the specification. Okay. But with fence, you can now write a code that uses the one-sided operations. And in fact, you could write a version, and we've got a version of the stencil code, which is coming up, that we can look at where you do a fence. You can use puts or gets or some combination to move data to the halos on the target processes, and then do another fence. Okay. So in fact, look at it like this. We set up an RMA window for each of those local meshes. The local mesh on each process, the window is made up of all of the meshes everywhere. Then we've got these origin buffers and the target buffers. And for example, I can do puts. If I really knew how I was making use of that data, and I could arrange it so that I knew what data I had locally that needed, for example, to be added into the data on the remote processes, I could do that with an accumulate, and maybe I could do away with the halos. The problem there is, remember, those operations in the accumulate are only the predefined ones. So if I need to do anything even a teeny bit different than what's already available, I'm out of luck. The idea here would be you have a version of the stencil code that makes use of these data types. In fact, and you've got ones that use non-blocking communication. Look at those and think about how I would replace that piece of code that does the exchange, which one that makes use of these RMA operations and put. Okay. And that's also, it's a good way to organize these things because the quality of the MPI implementations for the RMA can vary. So I can show you examples where the implementation does a great job with RMA, and I can show you examples where the RMA implementation is beyond terrible. And so you want to have that flexibility as much as you can. You can also do it with get. You have to be a little more careful with get because you have to make sure that you're getting data that's the right data, and so that you're not getting data that's too early or too late. Okay. So let me go on to the passive target model. So this is this lock and unlock one. Again, think of lock not as lock, because in fact it doesn't have lock semantics, but merely it's a begin or a start RMA on the origin. And unlock is complete RMA on the origin. So it would have been maybe better if we had done MPI win begin and MPI win end. Well, like I said, we always make some terrible choice of name, and here it is. But do note that the target process doesn't have to make any MPI calls, right? In the fence model, even if it's not doing any data motion, it still has to do that data synchronization call. Okay, so the routines, the basic routines look like this. So there's the win lock and unlock. There's you lock, so there's lock and lock all. So lock all is for all the processes in the window. If you just need to do operations to a single process, then you have to specify the rank and the window. Then there's a lock type. The lock type is either MPI win lock shared or lock exclusive. And that means pretty much what it says. If I do a lock shared, then other MPI processes can also be accessing that processes, the same ranks, processes, memory areas at the same time. If it's exclusive, then the MPI implementation will ensure that the operations happen exclusively. Now, that might be implemented by, for example, at the MPI win lock. This is why these are not lock and unlock. Might be implemented at the win lock, having that process where it said MPI win lock, lock exclusive, going and getting a lock on that process. But it is completely valid, and in some cases, far more performance appropriate for the implementation to say, great, I'm going to have to do a bunch of operations in exclusive mode. Let me record them all until I see the unlock. And when I see the unlock, I'll send the whole bundle and say, here, execute this bundle exclusively. And again, you want the MPI implementation to have the flexibility to make things fast, right? But that's why lock is a particularly terrible name, because it doesn't, in fact, require, even with lock exclusive, it doesn't require the MPI implementation to do what you think a lock means at that moment. Okay. Unlock unlocks it. There's an assert for a little bit of extra information. MPI 3 added flush and flush local. So issue here is, so I do the lock, I do some puts, some accumulates. Say I want to do a put and then do a get from some other data, and I want to look at that, and then I want to do another put based on what I saw. So for example, maybe I'd really like to do an accumulate, but my operation is too complicated. So I'm going to go get the data, do the modification locally, and put it back. Well, the problem with the lock and unlock is, remember, those operations are all non-blocking. So if I do that get doesn't complete locally until I do the unlock. So even if I was doing this exclusively, I'd have to do the unlock, which then means other processes can get in and do stuff. So MPI 3 added flush and flush local. And what those do is tell the MPI implementation, complete the RMA operations so far, but don't exit this lock, unlock, this begin, end region. So that allows you to start some RMA operations. So think of them as non-blocking operations you've got started, then you can say flush. And so here's a difference between, say, an ice and or a non-blocking collective in this is that for the two-sided, I would create a request and so forth, that I have await all. Here, for each of these puts and gets and so forth, there's no request object, there's no anything else. The unlock or the flush causes all of the previous ones to be completed. Okay? And then the flush completes at the target. The flush local locally completes at the target. Okay. So again, gives you fine-grained specification of just how much completion do you need. Okay, and so then, as I mentioned, there's also in MPI 3, there was this addition of lock all and unlock all. Almost by definition, this has to be lock shared because everybody's doing a lock. Lock exclusive, only one person essentially can do the operations at a time. So this is, it's all the processes. So there's no rank, there's no lock type. There's just this assert for a little bit of extra information. And there's also a flush all and a flush local all, sort of the corresponding parts. Most places where you might have used fence, you can use lock all and unlock all now. And so this is what's now recommended. This is a bit more powerful, particularly because of the flush operations, which you can use with these passive target ones. That again allows you a finer grain control over complete these operations. Okay, and then the last bit that I threatened you with before lunch is the memory model. And this again reflects MPI's focus on being fairly pragmatic and trying to provide the most performance. It also reflected the best and fastest architectures of the day, which was a long time ago. So there are probably some of you who weren't even born when that was done. So the original model for MPI essentially assumed that the hardware that would support these RMA operations would have some special local memory that it would manage, that the network would manage, and that it might be necessary to explicitly manage making that memory consistent with sort of the regular address space of the process. In fact, some of the fastest machines of the day effectively did this. So many of the Japanese vector supercomputers, for example, were not cache coherent. And they had software management for memory consistency. And they were they were really fast machines. I remember making a presentation at Los Alamos, and people were very surprised. Why don't we have machines like that? We've gotten better at providing coherency, although there are still a lot of trade-offs here. Anyway, be that as it may, the model is that there is the private copy and a public copy. The public copy that can be seen by other processes, the private copy that was seen just by the the home process, and that there'd have to be a moment where you'd have to make these things consistent. And so the MPI specification spends a fair amount of time talking about when that happens. This is similar to, but not identical to, some of the shared memory consistency models, particularly between processes. So that there are some related pieces there, and you will find an MPI win sync, which fits with this, but is actually really valuable for that one model that I didn't talk about, the one that allows you to create a shared memory window. when we did MPI 3, most of the hardware, the architects had put a huge amount of effort into supporting memory coherency and consistency. Even the GPUs had gone from models where they were separate memory models to having a lot more hardware support to try to manage this as a unified model. So MPI added an option to support this sort of unified model where we say, well, the hardware actually that doesn't have this artificial separation. But again, I want to mention this separation because, first of all, it's in the standard, so if you're reading about the standard, you know. But also, it, again, reflects real issues in the performance in the hardware, the real trade-offs. So making the memory look unified isn't free. It costs power, it costs die space, it costs a little bit of time. Many systems have decided that that's a good trade-off, which is why these days you don't have to worry as much about it. But even today, there are some of the fastest machines around don't do this all in hardware. They do some of it in software. Okay, so how much of this I want to say. I think I will mostly skip some of these details because most of the systems you'll be working with these days use the unified model. But if you are working with a system where there really is that separation, again, sort of recognize that MPI provides a way to essentially, again, control when it is you say, I need these things to be made consistent. Again, it's the same sort of model. We're trying not to over-specify it. It's expensive to ensure that the memory is moment to moment up to date. If I can relax that requirement, I can gain some performance, I can gain some simplicity, I can gain some power efficiency. Okay. Okay, so let's see, what else do I want to say here? Yeah, I don't want to go into this too much. Yeah, so again, the synchronization calls are points where these updates happen. So for example, to be completely portable, if you are accessing the memory that you got back from, say, WinAllocate, you shouldn't, you're not guaranteed to get the right result by simply allocating it. You should do a MPI win lock to your own rank to make sure that you access it. This is similar in shared memory to ensuring that something has done the appropriate memory fences. And in fact, those operations will ensure that those sorts of things happen. Okay. Right, so then I get to MPI win sync, which again was added in MPI 3 to allow you to say, I need to synchronize the window now. I don't want to wait until the end of the next MPI synchronization operation. Okay. So another thing that you can look at is now take that stencil operation, you've updated it with puts, or you've gone and looked at the code for put. Now you can replace the fence with lock all, unlock all, and the flushes. So the other thing here is that just as you do with, say, threaded code, so you could do sort of fine grain, you like single threaded, get to a loop, make a bunch of threads, get out of the loop, get out of all the threads. Or you can start a bunch of threads and arrange things so that I stay in those threads until I'm basically done. You want to do the same sort of thing here, is that you want to do a lock all of the code, all of the iterations, taking advantage of the flushes to do the local and remote completion. you don't do an unlock at the end of an iteration. You do an unlock when you are done, and take advantage of when syncs. You may need you need to think carefully about when do I know that the data is ready. So if I'm going to do a put, I need to know that the target process is ready for me to update the data. So you need to think about how you do that. That's why we mentioned a barrier here. There are other ways to do that synchronization that are not as collective but are more complicated. So again, you can look at this as showing a different way of doing the stencil operation. Coming back to, I can do this with point-to-point. I can do it with one-sided. Yeah. I do want to say that while a lot of the early one-sided work was really in the context of doing these sorts of stencil operations, this turns out not to be the best way to show off the one-sided operations. So I'm going to just take a quick detour before I finish up talking about some of the pragmatic issues on performance and finish this piece off. So the stencil operation can really be well expressed with two-sided communication. It's pretty clear where the data needs to go, where it's coming from. The coordination of the operations is actually important. All this stuff I've been saying about, well, how do I know that the target process is ready for me to give them data? One of the places where these one-sided operations become really valuable is where you don't have that kind of a constraint. You don't have that sort of ordering that's going on. So an example is I have a big array of data. It's too big for a single node. And so I have spread it across the machine, and I need to access information from this big array, but I have to access it pretty much at random. It might be a bunch of images, it might be an equation of state, it might be some data dump that I've gotten. In that case, two-sided communication is a pain in the neck, because as each process is running, it figures out what data it needs. And so it's got all that it needs to do a one-sided operation. To do a two-sided operation, it would have to communicate that need to another process and then coordinate moving the data. And so when you've got that kind of data, where only one process knows what's going on about the data it needs to access, that's where the one-sided makes a lot of sense. It can also be the case of, for example, you're creating some big set of data, and again, say each process is working out what it's going to add to that data set, and when it's done, it wants to deposit it. That's what a put is for, or if it's computing partial results, that's what an accumulate is for. And so the way to look at the two-sided versus the one-sided is not so much which one is faster. It's really, you should really look at it as which one fits the algorithm better. Yes?
We've been covering CPU architecture. Can we do the RMA with on GPU? Is there any standard that supports that right now?
Yeah, so the whole bit of the GPU to node to MPI to other thing is something that is actively being discussed in the MPI forum, which is to say that there isn't a standard for it right now. Different systems are at different states for that. So that's one where right now the best thing is to look at both the specifics of the systems that you've got, because some of them have some provide at least partial implementations of that. So there's a lot that needs to be done to make like MPI work from a GPU all the way to another GPU. And so the current state is that the current state is that most of it's unlikely to work directly. Some of it might. And again, I have to point you to, you've got to check, your particular system, your particular version of the software, because it keeps changing. The most portable thing to do right now is, I hate to say this, is still probably to use the CPU to do the data management and then do non-blocking moves to and from the GPU. There are cases, in fact, where that's faster than trying to use GPU direct because of other interference on the nodes. So I think my answer is that it's really complicated and that people are continuing to look at just what that integration looks like. It's one of the reasons I mentioned the memory models, because even though the separate memory model was not, was pre people's awareness of GPUs, it does have something in common with the different memory architecture on the GPUs, and some of those issues do carry forward. But I would say this is an area where things are still changing fairly fast, and it's a place where my actual recommendation is to think about this part of the code and isolate it, because that's the part of the code that's not going to be portable, that's not going to be standard compliant, that you're going to be taking advantage of wacko things that may or may not work in the GPU, and you'll want to have both. You'll want to have a backup, which is standard, and you'll want to, it was actually something we were talking a little bit at lunch about, is I expect there's going to be continued innovation there, which means it's going to continue to change. So I know that's not the answer you wanted, because I'm not telling you what you can do, but I am telling you that it's a mess.
Are there any OLCM platforms that come to your mind that have this type of setup?
Sorry?
Some platforms that come to your mind that have this setup?
Well, the NVIDIA GPUs have been continually improving in their memory integration with the nodes, and so being able to do some of these moves, there are MPIs which are GPU enabled that will understand when a memory location is actually on the GPU, and then they will do the right sort of things. But you need to make sure that the MPI knows, is implemented for that. Some of that has put the burden on the MPI implementation. That also adds, that's another thing it has to think about. But particularly for the NVIDIA GPUs, I think there's been a lot that's been done there. So that's where you probably have the best chance of finding something. Ken, did you want to add anything to that?
Well, I think, yeah, so you need a GPU-aware MPI. In general, if you have that and you give GPU buffers to MPI calls, MPI will do its best to detect that those are GPU buffers and do the right thing. Communication is still driven by the CPU using the standard MPI interfaces. There are examples of libraries like NVSHMEM, like NVIDIA's OpenSHMEM implementation, that have more sophisticated things you can do where you can kind of trigger operations directly from the GPU, things like that. That hasn't made its way back into MPI yet. MPI is still a very CPU-oriented API. So yeah, but we are discussing this. It may come eventually. NVIDIA is one vendor who's, like Bill said, is kind of far out in front of this, but there are other GPU vendors getting into the fray here, and we're trying to make sure we do something that works for everyone, not just NVIDIA. So yeah, the answer is it is complicated. But yeah, if you stick with kind of a CPU-oriented view of data movement, then the MPI API should work as long as, again, you know that your library is GPU.
Yeah, and I said this before, but maybe not clearly enough. We've been looking at even taking advantage of some of those, some of the hardware support on the NVIDIA GPUs, and even there, it's not as clear cut. It's not like, yes, now because you've got that capability, you should always use it. We've found that in some cases, it's better to use the CPU than the GPU because of very subtle ways that things interact with the memory systems and the network and so forth. So it's even messier than you think. Okay, other questions? All right, okay. So we try to talk about the standard most of the time. We're also trying to give you some pragmatic advice, and in fact, you just asked a good question for pragmatic advice. So a lot depends on the quality of implementation, and that is particularly true for the one-sided operations. And there's a couple of pieces to this. One is that you really want to be able to take advantage of the hardware. And one of the things that's interesting about the one-sided operations is that some of the more higher performing network hardware implements one-sided operations as in hardware, at least some subset of these one-sided operations. One of the reasons for that is early on, this was seen as a way to improve the performance of I/O operations to remote disks and things. And so that drove a lot of the early work, but just like with GPUs becoming more general, that work has also generalized. So you want to be taking advantage of the capabilities that are in the hardware. Now, having said that, the MPI specification is very general. It's got these great data types that allow you to specify virtually any layout. The hardware that's implemented for these one-sided networks is unlikely to be is unlikely to implement the full power of all of MPI in that hardware. And so understanding or finding out what's directly implemented in the hardware and in fact is implemented by a good MPI implementation by basically passing off the problem to the hardware versus what still has to be driven by the CPU because it's too complicated for the hardware because it's important. And another part of this too has to do with ensuring that things continue to happen, particularly in the one-sided operations, particularly in the case of the passive target. So one of the advantages of the active target model, the one with the fence, is that a bunch of processes could do stuff. They would do their puts or gets or whatnot, and they would all call fence. Okay? They would all call fence. That meant that if the MPI implementation needed to do something to complete those one-sided operations, it had been called. In the passive target model, the lock-unlock model, that doesn't happen. That means that if completing the operation can't be done entirely in hardware, but requires some code to run that's provided by the MPI implementation, then something has to cause that code to run. And so that gets us to the thorny issue that if you pay attention to the MPI forum discussions for very long, is called progress, is how much do we guarantee about the progress of these MPI implementations? And again, what are the trade-offs? So I'll just say a little bit here. So an advantage on the one-sided is the two-sided is actually fairly complicated. It's hard to implement, although there are some implementations that have in fact put the message matching into hardware, but it is non-trivial. One-sided, at least for the fairly basic operations, moving large blocks of data or possibly doing some of the accumulate operations can fit in hardware. So the challenge, though, as I mentioned, is some stuff will have to be done in software, which means some code has to be run by the MPI implementation, which means somebody has to cause that code to be run. And that's where we get into progress. So one way to get progress, and this also, by the way, applies to non-blocking two-sided operations. Because in the non-blocking two-sided operations, you're often sending around parts of the communication and expecting things to happen. How do those things happen? So one way is to set up a thread. There are different ways, maybe one thread per process. There are other ways to do this, where that thread has the responsibility of doing whatever it needs to be done to get these MPI operations to complete. In fact, some parallel computers have come with like weird numbers of cores, like 17. That's because it's 16 plus 1. That 1 is for that. Why don't all MPI implementations do this all the time? Because another theme I've been trying to say is that all these things come with trade-offs. And so if I have a helper thread, then I have thread safety issues. I've got lock contention issues. I've got other things that can impact the performance. And if I don't need that, then I've slowed everything down. However, because sometimes it makes things faster, sometimes you really need it. Many of the MPI implementations these days make it available. It is not always the default. So this goes back to, you may have to look at the documentation to understand. So for example, these are the MPI-CH-derived implementations. They've got ways through an environment variable to say that you need to do something else to support progress. So check the documentation for that. It can make a big difference. It can also make a difference for, again, non-blocking two-sided operations, non-blocking collective operations. But again, it might improve performance, it might hurt performance. Depends on what's going on. Okay. You can also try to get the hardware to help you. And so you can have the hardware deliver an interrupt when something arrives at the network. Some systems have done this and can get really good performance. Has to be done very carefully. Particularly interrupts that go through the operating system are expensive. Again, it's a lot of overhead, but if the timeliness of the operation is more important than the overhead of this, it can be a big help. That's why, rather than just give you something and don't worry about it, everything works fine. Again, MPI is fairly low level, gives you, the implementations give you that opportunity to tune for it. So to summarize, I've talked about the one-sided operations. I've talked about how sort of organize the MPI MPI code to take advantage of this with these MPI windows. They're collective over a group of processes, so you can use them over COM world, you can use them over subsets, you can use them over, for example, all of the processes on the same node that might share memory. We've got a variety of operations with different ordering and atomicity properties, so you can tune the code to express just as much as you need, given the MPI implementation, the maximum ability to achieve performance. There are a bunch of synchronization models. The two to remember are the fence, which is really good if you've got a bulk synchronous programming kind of application, and despite the fact that there's some disfavor with those these days because of some scalability limitations, they're actually really nice and they're easy to reason about, and they can be a really good choice, particularly at modest scalability. But beyond that, the the lock-unlock, particularly the lock-all and unlock-all, provides a very powerful and flexible model for doing these one-sided operations. And then finally, in order to get good performance, you do have to read up on the documentation to understand what it's going to take to get the MPI implementation to, in fact, provide the asynchronous progress so that the one-sided operations actually happen in a sort of one-sided manner. What I would ask you to do is not look at these yet, but they're here for you. So start by, since it's only 15 minutes, look at the non-blocking stencil code. Think about how you would change that to use put, where you would put the fences. And then, just to speed this up, once you've thought about that a little bit, go look at the solutions that are here.